In this example problem, we'll be applying the hydrostatic pressure equation to a sphygmomanometer, which is a very particular type of differential manometer which measures blood pressure. For simplicity, we'll be idealizing this sphygmomanometer as a simple U-tube manometer, as shown here, with one end of the manometer exposed to blood pressure, as shown on the left, and the other end of the manometer exposed to atmospheric pressure, as shown on the right, and denoted as P sub infinity. Mercury will be assumed as the working fluid in this manometer, as shown here in white, and air separates the mercury column from both the outside atmosphere, as shown here on the right, and from the actual blood pressure measurement, as shown here on the left. We'll be assuming that since the density of air is so much less than the density of mercury, and we're operating over such small distances d, the air pressure at this location right here where the blood pressure measurement is taken is equal to the air pressure here right above the mercury free surface. And in a similar fashion, the air pressure here in the atmosphere, so atmospheric pressure, is equal to the air pressure here right above the mercury free surface. So this entire air column is of equal pressure, and this entire air column is of equal pressure. So to formalize those assumptions, again, we're assuming one, that the change in pressure within the air columns is equal to 0. We're going to assume that a common blood pressure is approximately 120 over 80 millimeters of mercury. We're going to neglect surface tension, and we're going to assume a static fluid. And the objective here is to find the blood pressure, the common blood pressure listed in PSI gauge. So first, let's start with the hydrostatic pressure equation. So we'll look at our governing equation, and that's going to be P is equal to P naught plus rho g h, where h is the vertical distance between 2 points, right? So let's, for reference, draw our z-axis down here, positive z, and in accordance with the hydrostatic pressure equation, we have gravity acting parallel but opposite to the z-axis, g down. So if I want to look at the difference in pressure between my free surfaces A and A prime, the first thing I need to remember is 2 points at the same elevation in a continuous region of the same fluid are at the same pressure. So what does that mean? That means if I go to some arbitrary distance in z, let's say z naught, and I look at some point in my mercury right here, and then I stay at the same z naught and go across the manometer to this point right here, these 2 points are at the same elevation, or they are at the same point in z. They are at the same point in z, meaning what? This point and this point, since they're at the same z, they have the same pressure. And that would go for these 2 points and these 2 points. So effectively, what does that mean? That means that the pressure here at A is equal to the pressure right here at this point, a distance d from the free surface A prime. So what can we say? We could say that PA is then equal to PA prime plus the density of mercury times G times H. So at this point, we have to remember our assumption 1. Or in other words, there's no change in pressure across an air column because the density of air is so much less than the density of mercury. So the pressure of the air right here, where we're taking the blood pressure measurement, is equal to the pressure of the air here at the free surface A. So effectively, PA is our blood pressure. So what can we say then? We could say that if we want to express this in gauge pressures, then we could say PA gauge is equal to rho hg gh, where PA gauge is simply PA minus PA prime, where PA prime is equal to P atmospheric because of assumption 1. So as we just determined, PA is equal to P blood pressure because of assumption 1. So we could say that this is equal to P blood pressure, and that will also be in gauge. So this is the main equation that we want to work with. Remember, gauge pressure is just absolute pressure minus some reference pressure. In this case, our reference pressure, we're just saying is PA prime, which just so happens to be equal to P atmospheric in this problem. Okay? So P blood pressure in gauge is equal to rho hg gd. What is rho hg? Well, the specific gravity of mercury at approximately room temperature is 13.6. So 13.6 times the density of water at 4 degrees C is 1,000 kilograms per cubic meter. Then the magnitude of gravitational acceleration, we'll assume that we're on Earth and there's a standard gravity present. So that'll be 9.81 meters per second squared. what is D? D depends on whether you're referring to the systolic blood pressure, which is this first number, or the blood pressure of the blood as the heart is pumping, or the diastolic blood pressure, which is this number here, the second number, which is the pressure of the blood in between heartbeats. So the systolic blood pressure is this first number again, and that is the pressure of the blood as the heart is pumping, in the middle of a pump, so to speak. And the second number, the diastolic blood pressure, is the pressure of the blood in between heartbeats. And these are expressed in units of millimeters of mercury. So, in other words, this distance, when we're talking about millimeters of mercury, we're talking about millimeters of mercury along this distance d. So 120 millimeters of mercury is d is equal to 120 millimeters. 80 millimeters of mercury is d is equal to 80 millimeters. So if we're looking at our systolic blood pressure, we would say that d is equal to 0.120 meters, or in other words, 120 millimeters. So also remember that we're dealing with SI units right now, kilograms per cubic meter, meters per second squared, meters, etc. So the pressure of our blood pressure in gauge is going to come out as Pascal gauge, right? But we want it in PSI gauge. So we need to add a conversion factor, which we'll do right now. 1 PSI is equal to approximately 6,895 Pascal. And now we can compute our systolic blood pressure. So we plug these numbers into our calculator, and we get 2.32 PSI gauge. And again, that's our systolic blood pressure. And now let's repeat the process for our diastolic blood pressure. We're using the same specific gravity of mercury. We're using the same density of water. We're using the same magnitude of gravitational acceleration. The only difference is the distance d that we plug into the equation. So for the systolic blood pressure, we plug in 120 millimeters of mercury, or in other words, d, as shown here, is 120 millimeters. So A prime is 120 millimeters above A. For the diastolic blood pressure, we plug in 80 millimeters, or in other words, d is equal to 80 millimeters, or A prime is 80 millimeters above A. So we plug in 80 millimeters to this equation, and then we have the same conversion factor, 1 psi per 6,895 Pascal, and we get that our diastolic blood pressure is approximately 1.55 psi gauge. And just remember, the key point here is the millimeters of mercury refers to this distance d. So for the systolic blood pressure, we come out to about 2.32 psi gauge, and for the diastolic blood pressure, we come out to about 1.55 psi gauge. Okay, great. So that should be it for this video. Thank you very much for watching. I appreciate it, and I will see you next time.